Every week, a small plane operated by NASA flies over the basin of the Tuolumne River in the Sierra Nevada, tracing a path back and forth over the mountains, sensing snow from the air. This is NASA's Airborne Snow Observatory, or ASO. The goal? Provide water managers with near real-time information on the water stored in the mountain snowpack.
The function of our unit is to provide the water supply forecast for the spring and summer runoff that results from the melting snowpack in the Sierra. And that runoff forecast is used by a whole number of different agencies.
We deliver drinking water to the San Francisco Bay Area and neighboring communities. My group does the forecasting for how much volume is potentially available. So if there is available water that doesn't risk our water supply, we generate power with that. We also release water to the river when there's excess of runoff entering the reservoir.
For water managers, they just want to know how much water there is up there. So that's why we focus on snow water equivalent. So if you had a snowpack this deep and you melted it down right away, how deep would that water be?
The Airborne Snow Observatory is making the first measurements of snow water equivalent across an entire watershed using remote sensing.
It's a combination of two instruments that look out of the belly of the aircraft. A scanning LiDAR, which is a high-frequency laser pointer that measures how long it takes for laser pulses to return, and that tells you how far away the surface is. We can fly before there's snow on the ground and then fly afterwards, and the difference between those gives us a very accurate determination of the snow depth.
An ASO ground crew measures the snow's density to determine its water content. If you know the depth of the snow all over the river basin and how dense the snow is, it's possible to calculate the total amount of water stored in the snowpack.
The other instrument on board is an imaging spectrometer, which measures reflected sunlight in about 100 different colors. It's not increases in temperature that melt the snow, but for the most part, it is how much sunlight is absorbed by the surface. Well, isn't snow just white? No. It goes from absorbing only about 10% when it falls out of the sky, all the way to when it gets really, really dirty, it can absorb 70–75% of the sunlight that's hitting it.
ASO's measurements of the light reflected by the snow allow scientists to predict how quickly the mountain snowpack will melt.
And those two measurements together, the snow depth, which we turn into snow water equivalent, and snow albedo, the reflectivity, those two are key to understanding the timing and magnitude of snowmelt runoff.
That information is critical to the agencies that manage the water supply in California. Before ASO, most data about the water available in the mountain snowpack came from manual snow surveys. The data were spread out across the mountains and over time, and didn't include the snowpack above 10,500 feet.
Around April 1st is when we start to see the intense snowmelt come. Managing it, capturing water, generating electricity, meeting environmental metrics, running water down the river, this is a balancing act for those reservoir managers, and it's happening with the water coming out of the mountains very quickly. That they've been able to do as well as they have with the limited information in the mountains that we've had is absolutely remarkable. But with this greater and greater demand on the water resource, and also changing climate, which is adjusting the relationships that they rely on to estimate how much water is going to be coming out, it's an absolutely critical time to start to have better information.
The majority of our large reservoirs are dual purpose. They provide both flood control protection along with water conservation. The flood control people would like to have an empty reservoir, water supply people full reservoir, and having knowledge beforehand of how much inflow is going to result means that those reservoirs can be managed much more intelligently and serve both those purposes more efficiently.
When all of the inflows of the reservoir are back to normal summertime flows, we want the reservoir to be as full as we can so we can be prepared for an extended drought period like we're in now. Since the Airborne Snow Observatory had started doing its surveys above the Tuolumne River watershed. It's the first time that we have a complete spatial measurement of snow water equivalents across the basin. It's kind of been a holy grail for the snow monitoring community to have that piece of data set.
Much of the snowpack in 2015 was above the highest snow monitoring stations. ASO's data includes the high-altitude snowpack, giving a more accurate picture of the water stored in the mountains.
We take off in the plane, land, and within 24 hours, we've got a gridded snow water equivalent. We also have a gridded albedo or reflectance field, and those two combined are very, very powerful in terms of locking in that forecast. We can use that right now for forecasting.
That'll become very useful and powerful to organizations that really optimize power generation and flood control within their river management system.
ASO is showing the way to improving our knowledge of how snow and other weather phenomenon relate in a mountainous environment.
The agriculture and industry of California is built around the snowpack that melts every spring and flows down into the lowlands. So being able to have that information is better for understanding what the tools are that we have in our hands right now to make a change and assure the sustainability of our water system and the civilization as we understand it.
The knowledge and expertise gained in ASO is advancing our ability to measure snowpack from above. ASO opens the doors to using remote sensing in the Rockies and around the world, where snow is an important component of the water system and in many areas a critical resource.